Hey there, and a happy mathematical day in May we are having here. Boy, things are sure looking geometrical. I guess everything looks geometrical, right? You see boxes, which are cubes, and you see there's circles and triangles. They're just shapes all around us. Everything's geometrical. What's great to study this geometry a little bit, help us understand a few things. Today we are going to continue on with looking at different aspects of circles. We looked at chords, we looked at arcs, diameters, radius last time, and you guys just were killing it on the assignment. So good job on that. A lot of you, I can tell, was just going and looking it up, not paying attention to what I'm telling you, probably not even watching my video. You're just looking up because the definitions you were giving me on the differences between central angles and inscribed angles had some language that I hadn't talked about. So you know who you are. But that's all right. You're probably going to remember it better if you're seeing me demonstrate it rather than just looking it up somewhere on the web. So kudos to you for being here and seeing the live demonstration, because it's going to stick up here better later on when we quiz on this. Let's look at today's lesson. So today we're looking at tangent lines. We looked at chords. We looked at these other angles we talked about. We're going to look at something called a tangent line. And you're like, tangent? Wait a minute. We did sine. We did cosine. We're doing tangent again? No, this is a little different. This is with a circle. However, there is a relationship that continue into some higher math. You'll talk about this again. You'll figure out how the tangents that we talk about with right triangles tie in with the tangents we're going to talk about with circles. But we're not going to go very deep into that in geometry. But there is a connection. Okay, tangent lines. Swim to shore. Line L. Okay, here's line L right here. Represents a straight part of the shoreline at a beach. All right, so we're saying this is the beach. Out here's and say you're in the ocean out here at point C. This is you. You are point C. Hi, point C. How you doing? And you want to get to the shore as fast as possible. Maybe it's time to eat. Maybe you saw someone cute walking down the beach. Oh, I want to get over there as quick as possible. Whatever your reason, I'm not going to judge you. Assume that there's no current. Okay, so we're not fighting the current. The current's not helping us one way or another. Segments CJ, all right, C to J, and C to D are two possible paths you could take to get as quick as possible to the shore where you can hop up and start beginning on and running. So Diego says, no matter where we put point D, the Pythagorean theorem tells us that CJ, C to J, is shorter than CD, so CJ has to be the shortest path to the shore. Let me highlight that. CJ would be this path right here. Okay, and the other one is C to D. And he says it doesn't matter where we put D. Where? Because if D's over here, if D's over here, if D's right here, anywhere that we draw that line to D, this is still perpendicular. This is a 90-degree angle. So that pink line, wherever we move it, will end up being the hypotenuse of the right triangle used from the shore and this CJ. So since it's the hypotenuse, we know in the right triangle the hypotenuse is always the longest side. And so the longest side would not be the quickest path to the shore. So he says that CJ represents the shortest path to the shore. Do we agree with that? Explain the reasoning. Yes, we did, just because of what we talked about right there. Because if we had C here, put a point over here, put a point over here, wherever we want to put that, it's going to be a longer path than going straight perpendicular, right? Because perpendicular, a 90-degree angle, is going to be the shortest path to anywhere else we're going to put it wherever you want. Even if you put it right next to it, even if it's really close, doesn't matter. That's always going to be a longer path because it always ends up the hypotenuse, because the right angle right there is going to be the shorter of the two links in anything. So good job, Diego. You nailed that one, buddy. Let's move on. Let's look at this. So let's talk about a line tangent to a circle. I told you we're going to look at tangent lines. A line tangent to a circle. Oh, here's the important vocabulary part. Intersects the circle in exactly 1 point. 1 point and 1 point only. 1 point. So a tangent line will intersect the circle, but only at 1 point. Okay, so we have two different lines. Well, and a radius, right? It says name any tangent lines in this diagram. Okay, well, if we look at this line first, it intersects here and here. That's two intersections with the circle. That cannot be a tangent line. Let's look at this one. It only touches one place. That's a tangent line. But let's look at this one here, this radius. It only touches once, so is that a tangent line? No, because a tangent line talks about the whole line, not just a line segment. So if we took this radius right here, and we said, okay, I can see this part of it, but if I continued it like it should be to a line, not just a line segment, if it was a full line, it would also intersect there. So that has two intersections. That's two intersections. This has one intersection. There's only one of those lines that's a tangent line right there. So anything that's going to go inside the circle cannot be a tangent line. Cannot be a tangent line because it's going to have to touch the circle twice. Once on the way in, once on the way out, right? Because a radius would not count as a tangent line because if we extend that, it is touching twice. So let's look at a particular perpendicular. You love the little play on words they get for us here. All right, so draw a radius in the circle and mark the point where the radius intersects the circle. We're going to label it A. And then we're going to construct a line perpendicular to the radius. Oh, remember construction of perpendicular lines. We got to take it, make a circle, make those two marks, do the little thing, draw a straight line. It's a perpendicular bisector between the 2 points that we create with the circle. That'd be perpendicular. Yeah, I didn't bring a compass home. Actually, I do have a compass here, but we're not going to go through all the work. I've already created it right here. I just went ahead and saved us the trouble. So we create construction line that's perpendicular and label it L. So here is our line right here. I created it perpendicular. I didn't go through the whole construction marks. I got this off the computer real quick and easy. Okay, it says line L intersects the circle in exactly one point B. Right there, B. Why is it impossible for L to intersect the circle in more than one point? Why would that not be possible? Well, let's see. If we took another point on the circle, on the line, anywhere on the line, real close to it, over here, over here, over here. Anyway, we said this is a line perpendicular to the radius that goes through point B. That's the radius, and this is perpendicular. So this is a 90-degree angle. Right? That's a 90-degree angle. So that would be a radius because point B is on the circle. And if that's perpendicular to a 90-degree angle, if we want to find the distance of any other point on the line, any other point, I'm going to put a point really close right there. Okay? I'm going to draw this line from here to that point that's really close. Okay, that's really close. That's really close. Let's get right in and take a look at that one. All right, we can see that one's really close. Yeah, I want it really close. Would that also intersect the circle? It sure looks like it on our printout. That's just the width of the line there. If we had a skinnier circle and had this better, we could see. If we found the distance of that point, and let's just call that point C. All right, I made a point C right next to the B. If we found the distance of that, knowing that this is a right angle, which means it's also a right angle on the other side, this is a right triangle then. Even though the distance between B and C is really small, this still is the hypotenuse from A to C. Still has to be the hypotenuse. If we pulled it out here, it'd be a right triangle that's really, really small, right? That's a right triangle. So in that right triangle, this side is going to be longer than this side. The X side is going to be longer than the Y side because it's the hypotenuse. So if it's longer than AB, so we know that AC is longer than AB. All right, those two line segments, comparing those. If AC is longer than AB, what is AB? AB is a radius. That's a radius would be from the center to any point on the circle. Any point. The radius can be anywhere, right? Any point. So if AC is longer than that, it can't be on the circle. Because it's longer than the radius of the circle. It has to be just outside. That's so much. Just outside. Because it's longer than the radius. Does that make sense? Yeah, I think that kind of works. We kind of see that. Let's see if I can kind of get this back in some symbols that we can use here. All right. All right. So we can see. So what kind of line is L then? It's that wonderful tangent line that we just started today's lesson with. This is a tangent line. It touches only one place. It can only touch in one place because that would be the radius, and all the other points in the line to the center of the circle will be longer than the radius. Okay, fabulous. One more page we're going to look at today. One more page. I'm going to give us a little more space to see here. All right. Oh, well, there it is. Thought my glasses went bad for a moment there. All right, another angle. This image shows an angle whose rays, the two rays that come off the vertex, are tangent to the circle. Both the rays, okay? So starting at the vertex of this angle, the ray that goes this way, and a ray has one direction. This is a terminating endpoint, and it continues forever in the other direction. That's a ray. So this angle has two rays, and both of those, it says, are tangent to the circle, which means it only touches the circle in one point. One point perfect. So mark the approximate points of tangency. Well, let's see. I'm going to say that is about right there. That look about right. And this one we'll say is about right there. So those are the approximate points. That's about as close as I could get by eyeballing it. And once you draw the two radii, draw the radius, draw the other radius that intersect these points of tangency, and label the measure of the central angle. We studied central angles last time. So let's draw the radius to this point over here. And then let's draw the radius to this point over here. Okay, so that is the radius that connects to each point, right? And they're going to label the measure of the central angle that is formed. So this is the central angle that's formed. It formed this angle, this central angle. Remember, a central angle has the vertex in the center of the circle. And this is going to be angle W. So we've got angle W and we've got angle Z. So what is the value of W plus Z? Like, what do you mean what's the value? I don't have any numbers. But we do. They're just not written plainly right there. They're kind of go off what we know in geometry. And we got a lot of geometry knowledge. This is May. We've learned so much in geometry. We can figure this out. So we have, let's see if we can kind of define what we're looking at here. If we pay attention, we have a quadrilateral. If we look at all the four sides, kind of looks like a kite, pretty close. It looks like it's tangent enough to be a kite, but it's a four-sided shape nonetheless. We know it's a quadrilateral. And what do the four angles of a quadrilateral add up to? If you look at that and you go, I don't, just think of a square. A square is a quadrilateral. All quadrilaterals add up to the same thing. Like all triangles add up to 180. All those, it doesn't matter what shape, triangle, size, all those angles always add up to 180. Same thing with the quadrilateral. They always add up to the same thing. Since the square has 90 degrees, 9 degrees, 9 degrees, 9 degrees, 4 90s, 360. So all quadrilaterals add up to 360 degrees. So we know that. 360 degrees. That's our first clue. So we know these added together have to be less than that because there are two other angles. What do we know about those two other angles? It's a tangent line. What did we learn about a tangent line? Let's go back to this diagram before. The tangent line makes what kind of angle with the radius? It's a right angle. Every time, because it just touches one place, it's always a right angle. always a right angle. Go back to the very, very beginning of the lesson. It's always a right angle to go the shortest path. And since it touches the circle one place, the shortest path would be the radius. So this has to be a right angle. And since this is also a tangent line, this is also a right angle. So how much does a right angle equal? 90 degrees, right? So this is 90. And this is 90. So if those equal 90 each, how much is left for these? Well, 90 plus 90 is 180. So that's already used up by these two angles. So if we subtract 360 minus 180, that leaves 180. It means this angle plus this angle, the value of adding them together, has to be 180 degrees. This one may be 50 and this was 130. Whatever. We don't know that. We don't have enough information to figure that out. That we don't know. But we do know that added together, they have to be 180 degrees. There's no other alternative because this is guaranteed to be 90 degrees because this is the tangent line. This is guaranteed to be 90 degrees because it's a tangent line. And if both of those are 90 degrees, that only leaves 180 degrees for the other two angles, regardless of how much each one is individually. Together, they can't be more or less than 180 degrees. So, 360 degrees total, 180 with those two. Explain or show our reasoning. We did right there. We showed this is showing our reasoning. 90, 90, subtract from 360, it equals 180. So there you go. Now you know chords, you know arcs, you know tangent lines. We already know radius. I felt a little blurry there for a second. We know radius, we know diameter, all kinds of good stuff they're pulling out of circles, and some that we could hit on before in the year, right? Radius and diameter, but arcs and chords and tangent lines, all new stuff. But you guys are getting this really good. You understand arcs, you understand chords pretty well from looking at the work you've done on the earlier assignment this week. So I really think that tangent lines are an easy add on there. So until next time, do work you can be proud of. And let's finish the year strong, guys.